Welcome to another GCBASIC demonstration. This is part 16 for the 18FxxQ20 chip family. This time we're focusing on storage, and I'll explain what I call storage in a moment. So, like and subscribe to the video. Please let it run all the way through, but like and subscribe, otherwise there's no benefit. One day I'll get a penny from YouTube if you like and subscribe. Thank you. So we're looking at program memory, or Progmem, SAF memory, EEPROM, and data blocks. Different ways of storing something, data-wise, in your chip. And there are different areas within the chip. Let's have a look at that. So let me just do a recap of where I've got to. Descam. So I've got a Q20 sitting here underneath this cable here. Look, this is a programming cable. Here's a Q20, and at the top you can see there's a load of wires. But today, all I'm going to be doing is talking to it through the programming port, which is this cable here, which is up to a PICKit 2, and I've got a serial connection connected to my serial port, or I had it connected. I've just knocked it off, so I will put that back on for us. But essentially, that's all I've got running here. So I'm just going to put that back on. That's connected to B7, I remember. So connect that to B7, and we should have some serial communications in a moment. So basically, that's what we've got, and we're going to be using various different techniques to look at the memory. So what have we got in terms of overall the types of memory? We've got program memory, we've got data RAM, and data EEPROM. And those have different characteristics. Normally you put in your program memory, the program, you get the configuration, and you also get this area called SAF. It used to be called HEF at one point, and for some reason they've changed the name to Storage Area Flash, and it sits within the scope of the memory, what's called the program flash memory. And I'll peel that back for you. Within a chip, you've also got the RAM, the data RAM, and it's volatile. You turn the chip off and that disappears. But you've also got data EEPROM, and I consider that as a peripheral. In this particular chip range, it's 256 bytes. It can be more depending on what the chip is. But if you look at the diagram on the right, you've got these two red areas with respect to Progmem, program memory, and the data EEPROM area. Because data RAM isn't what we're talking about today. It's this area that is retained within the chip, what we're speaking about when we talk storage. If we look at program memory specifically, you can put your program in there. You've got some configs areas, which I haven't highlighted in that table on the right-hand side, but you've got this storage area block, and that sits at the top end of memory, and it has special characteristics for data retention, for long-term, write-protected retention. It's great. It's almost like EEPROM, but it's a different type of memory, and you can lock it to ensure it's never overwritten, etc. And if you put something in there and you protect it, you can't even execute against it. You can read it, but you can't execute code in there. So it's quite a clever area. Not really used that much, but it's a good area, and we'll be able to write to that, and we'll show you how we're going to write to that area. If I look at that, it's in the diagram here, it's at this area at the top of memory, as you can see here, at the top of the memory area, which is where we're going to be working very shortly. The other area is EEPROM, and I said we'll consider that as peripheral, and we saw that earlier on in the demonstrations around how you can write to the data EEPROM areas using something called EP write and EP read, and it handles it at the byte level. But I'm going to show you a different technique, how you can just push code, or not code, data into EEPROM. And so these different areas, you just need to figure out where you're going to put your reference data. Your program area, your program memory, the blue area, depending which compiler you're using, it could be like on the left-hand side, you get your program memory sitting from 0 memory pointer downwards. So let me just, it's actually upwards, but on the screen it's clearly downwards. This is 0 here and here. in both diagrams, and your program exists going upwards in that direction. But in some compilers, you get a little jump, and then the jump jumps you to this area here, and then your program is sitting in here. So depending where you are, you could put your reference data at the top of memory, like it says on the screen here. Here we go, I've lost my mouse here. Or you might want to put it at the bottom of memory, like in this one, depending on your compiler. GCBASIC is the left one. It puts your program at the bottom of memory, and you should put your reference data at the top. And you can use that for putting reference data in fonts, pictures, and other large amounts of data. So you can just load it in and read it back, and that's what we'll show you how to do. SAF is slightly different. SAF is also good for reference data. It's a larger area than EEPROM, but it's always in this same position. It's a specification. I said 128 bytes, but some of them are actually greater than 128 bytes. We'll have a look at this particular chip in a moment. And it always sits at the top of memory. So if you use this type of approach where you have a jump statement to your program, you must stop your program writing into the SAF area if you want to use the SAF area. You have to put an offset in your compiler to make that all work. You can do the same in GCBASIC. In reality, you just put a hash option in there and it will automatically increment the memory down to make sure it's not used. But you don't want to overwrite it, and you must adjust your program if you're not using GCBASIC. What about EE data? That's EEPROM data, and a thing called data blocks. Well, we have some special commands in GCBASIC that makes it extremely easy to write EEPROM data. It's called an EEPROM block or blocks of data, and you can use like a set of strings or numbers, and it will automatically get put into the programming cycle so that you don't have to use what we showed you earlier on in the demonstrations of EP write. You can just put it in and it will automatically put it into the programming code for you. And in reality, the same with what's called data blocks. You don't have to write very long programs to make GCBASIC write a huge data block out. A data block could be sitting right on top of the program, as in shown on the right-hand diagram, then the reference data could fill the rest of memory. It doesn't matter, and it's extremely simple to do. And I've seen many use cases since this implementation where people have put operating systems as reference data. Absolutely fantastic, but it's extremely simple to use. So what we've got is very simple methods for writing all these different areas, and that's into program memory, data blocks, EEPROM data blocks, and SAF. Extremely simple, easy set of commands. So we're going to look at some examples. We'll look at how we do program memory, SAF memory, EEPROM, and obviously these data blocks, and they're like blocks of data. So let's have a look what we've got. This is GC code, and I've got my demonstrations sitting there. So Control B just opens it up, opens the list, and I'm going to take demo 280, and we'll start with showing SAF data. We'll just have a look. And SAF data, it's all documented, so you don't have to really worry about it. Let's just visualize SAF for ourselves. So first of all, I'm just going to use my favorite programmer, which is PICKit Plus. And I've just typed in PICKit Plus. I'm going to open it up, and then we'll zoom in on that, and we're going to see and look at SAF memory. Let me see if that zoom is big enough for us. Oh, do that will show us. So what we've got here is a representation of the memory of the chip. And what I want to draw your attention to is these blue boxes. One says program memory, EEPROM data, and HEF SAF, 128 bytes. Oh, there's more than 128 bytes. I've just spotted. Look. You can have it as it's 1024 in this particular chip. Let me just try and I'll just resize the screen here so we can actually get it all on the screen. There we go. I've just resized it. Look. In here, there's a drop down. That drop down, oh, you still can't see it, but I can. Oh. goes to 1024. And if I look at it in memory in here, I'm going to pull down, it's in a different color. It's in yellow, background is yellow. And as I change the block size, that yellow gets larger and larger. And that is the managed part or SAF area of the chip. And they come in 128K blocks, and this one has got quite a few blocks. And it's quite tough to write to it, but I'll show you how we do it quite easily. So I'm going to leave that at 128, and that will just say to us that the first byte, or first word, sorry, of HEF memory is a FF00, the hexadecimal number FF00. And if I look at the program we've got, I've got a program here that it's going to do some clever coding for us. I'll bring that across so that we can see it. Get it absolutely lined up for us. There we go, great. We got a chip. We said that before, 16F, 18F16Q20, and I've got the PPS peripheral support, and I've got a USR set on B7. Okay, and that's just turning on the serial on that particular port. The rest of that sets it up. And here we go, look, I want to write something into the SAF memory, and I've created an 8-byte array called my buffer, and it's got some numbers in there. And we're going to write those directly to the SAF part of memory. Anything to do with H serial print is going to put it on the terminal, so that's for information, and we'll have a look at that. And down here, there is a write block, and it says here, SAF write block 0, my buffer, and that is the buffer I'm going to send to it, and the number of bytes, and the number of bytes is 8 bytes, and I can see that from this variable here. So what I've got is my buffer, series of numbers. I have a variable called my bytes, number of bytes, which is 8, and then I'm going to write that out. And essentially, I can then write it out using SAF write block into block 0. It's actually offset 0, and it's always offset 0 from the lowest SAF byte. And then I can read it back. And the rest of this puts it on the screen. So if I program that, we're not going to look at the serial terminal. What we're going to do is we're actually going to read the chip, because it's easier to see it in the chip. So in here, it's programmed it. If only it had. I had a warning. Why have I got a warning? Pass. Probably because I actually tried to do a write. It's now successfully programmed it. If I read that back in using PICKit Plus or your favorite programmer, I don't care which one, and we look at the address, which is the first word of SAF memory, we will see a set of numbers appear in here. 2C20, 2C20. Let's look at our source data. Here we are, 2C20, and it ends with 633F. It ends with this one here, 636F, because it's actually written 8 bytes in. And then later in the program here, I write more numbers out. I write more words out. Look, I write out these words at different areas. So I'm putting 4 more words into SAF memory by using SAF write. And essentially, I'm saying here, SAF, you can just write words into a particular location. If I write a word, this is a word variable, I can just put it at any location in the SAF memory by using SAF write word. And on the terminal, if I cursor out to the terminal, once I start it up, function key F9 will start the terminal. Here's the terminal. I connect to the terminal. Now, if I just reset the chip, this is all the information that was put out there. And it says there that you would find these values in the memory of the chip. And if I look in here, inside of, you'll have to ignore the red there because I forced that error. It says in here, it would expect to see the address here is 2C20, F through to 4231 at the end, look, 4231 at the end. And I can see that this address here of FF00 is different from this. Is it the same? Now, yes, it's the same, FF00. So I've read it in and displayed the SAF memory on the serial terminal. So we can see it both ways. We can say we can prove that we've written it by using PICKit Plus. We can prove we've read it by putting it on the serial terminal. So we've written to a particular area. Now, what's interesting is that some programmers protect this area of memory. In particular, PICKit Plus does, it protects that area. So if I now try to write out, I'll just change this number here to whatever. If I actually write that out, the first thing it will do, it will cache the memory of SAF. It will read it in and write it back. And in that way, you don't lose anything. So in the programmer here, you've actually got enable SAF auto merge. So what you've got is ways of writing out SAF memory, programming it, and not have it overwritten. Investigate that in your own time. Let's look at another demo. Control B. That was 280. 290. Showing program memory. This is program memory. So what we're going to do in here, we have a set of routines called PFM read and PFM write, and we can just read and write all the memory from the word 0 right to the end of the chip. Then in this program, I write some data out to an address called 3FF8. I'm going to put the number 11 in there, and then I'm going to write out to 3FFC 55AA in hexadecimal. And so what we've got is some very simple commands called PFM read and PFM write, and they will write out words for you. Very simple. And these are historically what was in there. And then there's a dump from this application into the serial terminal showing you what it's found. Now I will read that back in using PICKit Plus. I will then cursor down to 3FF. And whilst it's still reading it, I can position the cursor. And here it says it hasn't got anything in there from the last read and write. And all of a sudden, if you look very carefully in the middle of the screen here, we've got FF11, which is what we wrote, and we've got 55AA. So we're writing explicit words into program memory. Obviously, be very careful with this because you can overwrite your program, but you can put reference data in there and etc. into any part of memory. And remember, let's have a look at what's happened down here in our SAF memory. Our SAF memory has been overwritten by the programmer. So you've got this balance here. The serial terminal is also showing us what it found. It says it found something at 00 through to 1E. And what did it find? It should find our program sitting down there. It starts at EF06 and an address. It says it found 6E0D at that address there. So you've got ways of reading the program memory using these utilities called PFM write, PFM read. Very simple commands. But what happens if you've got bigger blocks of data? More blocks than that. Let's have a look at demonstration. Another demonstration, which is really how you can write much larger blocks of data. And you don't have to know all those commands. Well, essentially what you've got here is this block called EEPROM. You've got another block called data. And they start as with the EEPROM, starts with the EEPROM, and then a name, and end EEPROM. And everything in between is just put into your EEPROM memory. You can give it an optional parameter and say, my EE data 2, I want it at location 16. Could be a hexadecimal number, in this case it is not. And you can put this data directly into EEPROM and it will automatically then program it for you. But what about if you wanted to put a huge amount of memory, you use a huge amount of reference data like an operating system. Well, you'd use a larger data block and you give it a name. You can put it in as bytes or as words. The default is words. And you can just stream the data in on the top of your program memory. Let's look at this. Function key F5 to program it. So what we're going to do is we're going to read in, to start with, just the EEPROM. Now, serial terminal in this demonstration is displaying stuff, so you should look at that as well. So I'm just going to read that in, and all I'm doing now is reading in the EEPROM. If we zoom in on that, we can just see the EEPROM. Let me just have a look at the EEPROM there. There's the EEPROM, and there's the values we put in it. I'll try and put them on the screen at the same time. There we go. 1, 2, 3, 4, 5, something, put that in there. Well, if we look at our source code, we have these values, oh, sorry about that. 1, 2, 3, 4, 5, 255. And that's exactly what we got at this address here. And then underneath that, in the code, you can see 54321, 255, and there it is, 54321. And there's no other configuration required to make that work. But what about these other reference blocks called data blocks? Where are they sitting? Well, if we look in here, we're looking for something that looks like 1, 2, 3, 4, 5, 6, 7, 8. And I click on the program and we go to the top of the program. I already saw them zip past. I can see that one there. That's 1, 2. Oh, I didn't read it in. I'm just going to reread the memory because I did remember I only read the EEPROM. So read. So that's where the old top of the program was at 0978. And now we're going to look at another program with this reference data on top. And here we go. And here it is. Like it says here, like 0, 1, 2. Here it is. 1, 2, 3, 4, 5, 6, 7, 8. It's all there. All the data's there. Let me just show you again. Here it is. 1 and 2, 3 and 4, 5 and 6, 7 and 8. But what was the next reference block we got? 1, 2, 3, 4, 5, 6, 7, 8, and this is the hexadecimal numbers, which were below here in red. So you can easily put reference data into your program. And if we have a look inside of the assembler for this particular piece of code, we look at the assembler by pressing function key F7. We can see these in the assembler themselves. And here it is. It says here my data block number of items were 8, and here is the actual data block it put in there of those numbers that were in our source program. My data block number 1, and it put it on the screen there in this assembler. And here is all the information that we put into our EEPROM. The first block went in at address 38000. It calculated that automatically. And the second one, he gave it an offset of 16, which is hexadecimal 10, and it would have put it therefore at 380010. And there are some data words. Fantastic. It is so simple to use reference data, program memory, EEPROM, EEPROM data blocks, and data blocks with GCBASIC. It is very, very simple. That's what I wanted to show you in this demonstration. These demonstrations are obviously within the install are all available for you to have a play with. And I'll just check there's no others I should be showing you. No, because remember all this information is also being sent out to the serial terminal whilst we were looking at it in there as well. So you can have a good play to see how those functions are working. Next time, we're going to be looking at using CLC, configurable logic blocks. And then we're out the back of this demonstration. There are other demonstration source code in there. Please enjoy.